in the 1-minute summary is that, so it's supposed to be some extension of Riemannian geometry, the mathematical formalism that underlies general relativity. In Riemannian geometry, you specify a geometry by giving two things, a manifold and a metric on that manifold, okay? So I first tell you the manifold, which tells you the topology or the differential topology, really, of the space that I'm interested in, and then the metric defines lengths and angles, and so that I'm really working with geometry. Okay, so non-commutative geometry is a subject that has been developed since the 80s in the mathematics community. It's some sort of extension of Riemannian geometry. And here the basic input that you give is something different. You give a so-called spectral triple consisting of an algebra and a quote-unquote Dirac operator D acting on a Hilbert space H. Okay, so let me just remind you, as George said earlier, all that an algebra is a vector space where you can multiply two vectors to get another vector. So for example, n by n matrices are an example of an algebra. N by n matrices, let's say over R, well, I can take linear combinations of two n by n matrices and get another one, so they form a vector space. But I can also multiply two matrices to get another one, so they form an algebra. Okay, so you have an algebra, and then D is just this algebra is going to be linearly represented on some Hilbert space H in the usual approach. And then D is just another Hermitian operator that also acts in the Hilbert space H. And the idea in brief is that A, roughly speaking, is you should think of as like the algebra of coordinates over your manifold. So this is kind of encoding the information that you used to encode here, whereas D is defining lengths on your manifold. So it's encoding the information that you used to encode this way. Unfortunately, that's all I have time to say, or Laurent is going to get upset at me. So if you want to know, if you want to understand that better, ask me afterwards, and I'll tell you more or give you something to read. But so that is what is non-commutative geometry. So then why is a physicist like me interested in it? Well, people have been interested in non-commutative geometry. Physicists have sort of for a long time, in the sense that, ever since we learned from quantum mechanics that phase space was, once upon a time we thought it was a normal manifold, but then quantum mechanics taught us that no, it's some sort of weirder thing. It's some non-commutative manifold. So what is the appropriate mathematical formalism to describe that? And when you're trying to do quantum gravity, for a long time, there has been this idea that in some sense, at the Planck scale, space-time itself should manifest some sort of non-commutativity. So that's really not the main motivation for me. The main point for me is that it does a better job in some non-trivial ways of describing the laws of nature as we currently know them, in terms of, that is to say, it gives a more concise and more, in various ways, more explanatory account of the standard model of particle physics coupled to gravity. And here I'm talking about work dating from the 90s due to Kahn and Lott and Shamsuddin, and then also very important contributions from Matilda and John, who are in the room, and then other people, Dubois-Violette and Lisi and a bunch of people at Marseille, and I'm probably forgetting some people. But okay, so let me just briefly say what I mean by that. So the short story there is the following. So let's do a side-by-side comparison. Laurent, you can just prepare your talk or catch up on sleep from your flight or something. He's really heard this exact thing too many times. Okay, so in the normal approach, in the approach where I regard, space-time as being described by ordinary Riemannian geometry, and then physics as being described by fields, quantum fields living on that geometry, the basic framework of effective field theory, then if I want to tell you what the standard model of particle physics is, I have to do it in 3 steps. Okay, so step 1, I tell you what the symmetries are. In particular, I tell you what the gauge group is. So I tell you it's SU3 times SU2 times U1. Okay, and then step 2, I have to tell you what are the fermions in the theory and what are their how do they transform under the gauge groups. I have to make a little table here. So I have to list for you what are the fermions in the standard model. And so there's a left-handed quark doublet, up left and down left, and there's a right-handed up quark and a right-handed down quark, and there's a corresponding leptonic sector. There's a left-handed lepton doublet, and then there's a right-handed neutrino and a right-handed electron. Those are the irreducible multiplets. And then I have to tell you I have to fill in this table to tell you how they transform. So I have to tell you as an input that the quarks transform as triplets under SU3 while the leptons transform as singlets, that the left-handed guys transform as doublets under SU2 while the right-handed guys transform as singlets. And then there's some U1 charges that I also have to fill in for you. Okay, so that's step 2. And then we're not done yet. You're not ready to write down the Lagrangian yet. There's step 3, which on this side is a completely independent step, which is what are the scalar fields in the theory? So what are the spin 0 fields? So I have to extend this table and make a list of all the scalar fields and their charges. So, well, it's an unexplained input in the ordinary approach to the standard model that there's just one extra line on this table, the Higgs doublet, and it's a singlet under SU3, doublet under SU2, and has some hypercharge. Okay? So that's the basic data I have to give you on this side. So then let's compare that to what I give you in non-commutative geometry.
We need a kind of simple question. When you put 1/6, what do you mean?
That is you should think of this as the electric charge, it's really the hypercharge. But so when you say the electron has charge for the right-handed particles, this is really equal to the electric charge. The right-handed particle has charge -1, quark has charge plus 2/3 and minus 1/3. The left-handed doublet has charge plus 1/6. Okay, so on this side, well, we can still think of it as being 3 steps. Step 1, I have to tell you the algebra. Remember, that was the first object in my spectral triple. So in particular, I have to give you a certain finite dimensional algebra. I choose a certain finite dimensional algebra. I tell you that the algebra is the complex numbers plus the quaternions plus the 3×3 complex matrices. And then so secretly, I'm choosing this algebra to get this gauge group. It turns out this gauge group is really nothing but the unitary group of this algebra. So I'm putting in, then step 2, I have to tell you the representation of the algebra on the Hilbert space. So I mentioned the interpretation of this and this. These guys both act on the Hilbert space, which physically is going to be the Hilbert space of spinors living on the space-time defined by these guys. So anyway, I have to tell you suppose I have an element of this algebra, lambda qm, where lambda is a complex number, q is a quaternion, and m is a 3×3 complex matrix. Then I have to tell you how it's going to act on the Hilbert space, on the finite dimensional Hilbert space. And so let me just be a little bit explicit here. So it's just some block diagonal matrix that if I use this notation that Q lambda is the 2×2 matrix that has lambda and lambda bar on the diagonals, lambda complex conjugate on the diagonals. This matrix is Q lambda, lambda m, q, q. Okay? And so this is, obviously the details are not important here, but if I had written this fully notated, you'd be able to count up that this is just a 32×32 matrix. So it acts on some 32 component vector space, 32-dimensional vector space. And that's not a coincidence. That's because 32 is the number of fermions over here if you take into account, if you count color and the two different helicities, two different chiralities and particles and antiparticles. Okay. And now, so in other words, here I've really put in all the information I put in here. Here I've really put in all the information I put in here. But step 3, there's a difference. There is no step 3. Okay, so once I've told you this information, there is a crank I turn to compute simultaneously what are the gauge bosons and what are the scalar fields. So just like over here, once I told you the gauge group, I could determine what were the gauge bosons and how they transformed. Over here, once I've told you the algebra and its representation, both the gauge fields and the scalar fields and their transformations are determined. Okay, so that's a big improvement over this, where there was a completely independent, the Higgs sector was a completely independent third unexplained input. Another important point to say is that there are various things that are improved in the fermionic sector. So because over here, the basic input is a group, and over here, the basic input is an algebra. And the representation theory of associative algebras is much more constrained than the representation theory of groups. So over here, there are various things you might ask about this table that are unexplained on this side. Why is it that all the particles either appear in either the singlet or the fundamental representation of these groups? I mean, there's an infinite number of representations to choose from, the singlet, doublet, triplet, etc., of SU3. Why do you only see 1 and 2 appearing in this table, or 1 and 3 in this column? Why is it that there's only 2 non-abelian groups that appear here? How come no fields transform under more than 2 non-abelian groups? Those are all unexplained inputs in the ordinary approach. They're not the unexplained inputs that people normally focus on. Physicists have been obsessed for decades with other problems with the standard model, the hierarchy problem and the cosmological constant problem. But it's important to remember that there are really all these unexplained inputs. And so those various things I just mentioned are explained outputs on this side. Okay? So, so the point of this talk is just to say, I take that, and I haven't given the whole list here, but I take those things and a few more things like them as rather non-trivial evidence that non-commutative geometry is providing a more apt framework for describing the laws of nature. But just like there are unexplained things here that are fixed up here, there are unexplained inputs and assumptions in the non-commutative geometry construction. And I want to ask if you can go further and find an even better framework, a reformulation that does an even better job of explaining more with less. Fewer assumptions, fewer axioms, fewer choices and things you have to put in by hand. Okay. And so that's what I want to get to telling you about. So let me start by setting the stage by saying a little bit in more detail about what are the inputs and axioms, assumptions that go into non-commutative geometry, and which of them are sort of unstated assumptions, which of them are axioms, and which of them are extra inputs you just have to put in above and beyond the geometric axioms, just by hand to get the right answer. So just to make a quick list here. So again, the inputs. Well, we have to the basic ingredients. We have A, which is a star algebra. We have to have some Hilbert space H, some Dirac operator D, which is going to satisfy a bunch of axioms. In particular, let's state right now that it has to satisfy that guy. And this is, I should say, normally taken to be associative, meaning that the product in that algebra is associative. And then there's 2 other important inputs that the axioms for non-commutative geometry have kind of grown and evolved over the years as the mathematical formalism has been made more self-consistent and kind of deepened, and also probably in part with an eye to the fact that with an eye to its connection to physics. So 2 other. Once upon a time, the input was a spectral triple, but really nowadays there's 2 other important ingredients you have to put in. One is an operator J, which also acts on the Hilbert space. This is an anti-linear unitary operator, an anti-unitary operator. So in physics language, this thing is what you would normally call charge conjugation. It's the operator, it's the anti-linear operator that, if I just take a spinner and I take its star, this thing transformed correctly under Lorentz transformations, but this thing in the normal helicity basis doesn't. So you have to multiply by I gamma 2 to correct that. So this is what I would call J psi in Lorentzian four-dimensional spacetime. And then gamma, this you can think of as defining the orientation on your spacetime, a notion of left-handedness and right-handedness, and it's what physicists would it's the analog of what physicists would call gamma 5, the chirality operator, which splits fermions into left-oriented and right-oriented ones. Okay, and then these guys have to satisfy a whole mess of axioms for the theory to be consistent. Okay, so the normal assumptions that go in are that. So let's see. I don't quite know how to number these, but just to be explicit. So there's an associative left representation of the algebra on H. There's also an associative right representation on H. The left and right actions commute with one another. That's usually known as the order 0 axiom. Then the left and right actions are normally related, taken to be related, not independent of one another, but related via the antilinear operator J in some way. In non-commutative geometry, the algebra elements are regarded as like the 0 forms on the manifold, but then there's 1 forms, 2 forms, etc. And so for example, an object dA, a 1 form, the differential of the 0 form A, that in non-commutative geometry that acts from the left on the Hilbert space by this formula. And then there's a corresponding way that that differential forms act from the right, and et cetera for higher order forms. And then there's various other things. I'm not going to go on and on forever. I just want to emphasize that there's a long list. So let's see. J squared. Another axiom is that it's taken to square to epsilon, where epsilon is a sign, plus or minus 1. J is taken to J and D, this is another sign, epsilon prime, plus or minus 1. So J either commutes or anti-commutes with D. J is taken to either commute or anti-commute with gamma. That's a third sign, plus or minus 1. And then in the actual construction of the standard model, you end up having to choose epsilon equals plus 1 here. And in the actual construction of the standard model, you end up having to also choose epsilon prime prime here equals plus 1. Okay, and those two choices really end up choosing the dimension of spacetime in non-commutative geometry. So these end up fixing the signature of spacetime to be 0 mod 8. So this is really saying, in other words, this is really fixing the geometry to be, there's a 4-dimensional continuous part which has signature 2, it's 3, 1, signature, it has dimension 3, 1, so it's Lorentzian 4 dimensions, and then tensored with a 6-dimensional finite space. So this is really saying that the whole space, when you add the 2 up, is a 10-dimensional space, so 9, 1. And that's in order to get the standard model construction to work, and those two signs you have to choose. And okay, so there's maybe I'll just say 2 more. Gamma and D are assumed to anti-commute, and gamma is taken to commute with both the left action and the right action. And then this is not the end of the list, but this is where I will stop. I want to emphasize to you that there's a rather long list that have been accumulated kind of more over the years, and they all play an important role. But you know, there's kind of when presented with this, it gets to be rather a long list of input data and axioms, kind of in a bit of a hodgepodge quality. So I want to say that there is a rephrasing of this, that the repackaging of this, in which this set of elements and these axioms get condensed into a significantly smaller set. And in that repackaging, you also get additional constraints, which perform for you a bunch of the make for you a bunch of the choices, automatically make for you a bunch of the choices that you have to make in the construction of the standard model that are not axioms. I actually mentioned already two of them here. Here are two choices you have to make when you choose the dimension of space-time usually, but that'll get chosen for you by this reformulation. And then there's another important improvement, another important thing where normally you have to, it's not fixed by the axioms, you have to fix it in order to get the standard model right. That will get fixed by the reformulation automatically. Okay. So what is the idea? Where to start with the reformulation? Well, you know, we were interested in, one of our main starting ideas was that, you know, that we should go non-associative. That in quantum field theory, in normal quantum field theory, you know, the basic input is a group, and you know, the gauge group, let's say, and the symmetry group, and in particular the gauge group. And already back in the 1920s, you know, Weil had understood that electromagnetism could be understood as gauge theory with gauge group U1, a commutative group. And already at that point, you could have begun asking yourself, you know, well, what would happen if I tried to build gauge theory with a non-commutative gauge group? But at that time, physicists didn't do that because it was regarded as a, I don't know, it was kind of regarded as a, physicists at least looked askance at that time on non-commutative gauge groups, and they just thought everything was going to fall apart if you tried to somehow make a non-commutative analog of electromagnetism. But nowadays we know, you know, if we did some then and 40 years later, Yang and Mills found Yang-Mills theory, and you know, now of course we know that we would be missing a lot about mathematics and physics if we didn't know about Yang-Mills theory. Somehow groups are naturally non-commutative, and you're missing a lot of the most important groups if you restrict yourself sort of artificially to the associates, to the commutative case. Well, there's a very analogous thing you might say about algebras. In algebras, groups are naturally associative, but algebras are not. I mean, a lot of the most important and beautiful algebras are non-associative algebras. Lie algebras, Jordan algebras. In particular, there's this jewel called, there's this amazing algebra called the exceptional Jordan algebra. And there's the Actonians. There's a lot of very important, it's very analogous. Algebras are really, should not be constrained to be associative. I mean, of course, a lot of interesting things to be understood about associative algebras, but algebras should be left to breathe, and they want to become non-associative. So we wanted to rephrase, we wanted to ask, is there a way to rephrase things so that it's appropriate to the non-associative case? And, you know, the first problem that presents itself is that, am I right?
No, that's fine.
The first problem that presents itself is that, well, the first step here is that I'm supposed to take, in the usual form, spectral triple formulation, is that I take my algebra and I represent it on a Hilbert space H. So usually what you think of that meaning is you take every element of the algebra and you map it to a matrix so that the product on the algebra is represented by the product between the matrices. Well, but that can't be right. That doesn't sound good because the product between matrices is an associative product, and so how could you ever represent a non-associative algebra that way? So already in the 40s, while he was taking a break from inventing category theory and the algebraic homology, Samuel Eilenberg, gave a very nice answer to this question, what it means to represent a non-associative algebra. He said, okay, so suppose you have a non-associative algebra A, and you want to represent it on some vector space H. Well, let me just define, for starters, that what I mean by a representation here is nothing but a bilinear product. So where I can take any two elements, any element from A and any element from H, multiply them to get an element in H. I'll call that the left action. And then I have another bilinear product, a priori independent, where I take the two elements. It's a different bilinear product, so I'll write it this way with the A on the right action, and again get an element of H. And he says, well, if that's all a representation is, then a representation is really nothing but a new algebra B, called B naught, which at the level of the vector space is just the direct sum of the vector space A and the vector space H. And then it's equipped with a product. So if I take two elements, if I write an element of B as A plus H, then the product of two elements here okay, so if I just write the product here and I distribute, well then this is nothing but the product that this gives me back an element in A. It's nothing but the product inherited from the algebra. This gives me an element in H. It's nothing but the left action I just defined. This is nothing but the right action I just defined. And this guy is 0. Okay? So he says that's how I'll define a representation. But now I haven't yet said anything about A being associative. If I do, now if I declare that, and so in particular, this is a definition of representation that is more general than the usual definition of a representation in algebra. If I take B naught, if I now demand that B naught is associative, then I recover the usual associative definition of a representation. In particular, if I define the associator of three elements, A, B, C, be A, B, C minus A, B, C, then all the associators in this algebra have to be 0 in order for it to be associative. So in particular, this associator has to vanish. Well, that recovers the usual assumption that A is associative. This associator has to vanish. Well, if you think about it, that recovers the usual definition of a left action where the multiplication is, in the algebra, is represented by composition of the matrices on the Hilbert space. It's the usual thing I described before where matrices represent algebra elements. So that says I have an associative left action. This associator says I have an associative right action. And this associator, one where I put an H in the middle, says that the left and right actions commute with one another. And so you'll recognize that that those four extra conditions I get back by demanding if I define representation this way, I could just never demand that B is associative. The whole thing is set up to make sense even when B is not associative. But if I do demand that B is associative, then the four non-trivial associators I get from that condition give me back the usual NCG assumptions that the algebra is associative, that it's left and right represented on H, and the so-called order 0 condition. And so that sounds like a nice starting point. It sounds like a generalization that gets back something about the usual case. So let's go one step further. Let's imagine we asked that B naught was not just an associative algebra, but an associative star algebra. I remind you that a star algebra just means an algebra, or that there's also a star operation, like complex numbers. Complex conjugation is a star operation on that algebra, or matrices taking the dagger is a star operation. It has this property that if I take the product and I take the star, it's an anti-involution. It's an anti-automorphism on the algebra. So it does this, and then if I square, I get the identity, and it's antilinear over the field that defines the algebra, field over which the algebra lives. So, well, let me just say one thing about this. Notice, okay. So it turns out that if I just demand that algebra is a star algebra, that gives me back then automatically those two conditions I just wrote down give me back this guy. This comes from the anti-automorphism property that the right action and left action are related this way. It gives me that j squared is equal to epsilon, and in particular, okay, let me back up a second. So in modern language, this thing is a superalgebra. It's a Z2 graded algebra. So this is that's just what this multiplication law says. So this thing is the even part, and this thing is the odd part. And the star operation had better respect that Z2 grading on the Hilbert space. So in order for it to respect it, the star operation has to have the property that if B is equal to A plus H, B star is equal to A star plus JH, where this star operation has to be, this thing has to be a star operation already on H by itself, and this has to be an invertible antilinear operator from Hilbert space to itself. That's disrespecting superalgebra. So that gives me back a couple more things here. That gives me the fact that the star operation has to square the unity. That gives me, that tells me what, that's where J came from. That's why J is in the game. It tells me that that's the square to epsilon, and in particular epsilon equals +1. And what else does it tell me? Oh well, then it tells me that A is a star algebra, not just any old algebra. Okay, so the fact that B naught is an associative star algebra has already done a pretty good job of recovering a bunch of sorted things on our list here. But in non-commutative geometry, it's not enough to just represent the algebra, the zero forms on the Hilbert space. You want to represent differential forms, in particular, like in the gauge fields and also the Higgs fields in non-commutative geometry language are going to be given by one forms on the geometry, and so acting on the Hilbert space, interacting with the Fermions. So we want to not just represent A on H, but we want to represent omega A on H. And so the question is how to represent omega A on H. Well, Shane and I, we thought just taking Eilenberg's formula was so good, seemed to be working so well, just defining this thing. That seemed to be working so well. We thought, oh well, we'll just erase the zero here and replace A by omega A here. So omega A, I apologize, I didn't say what omega A. Omega A, so associated to any algebra, associative or non-associative, there is a universal algebra of a universal differential graded algebra. So what I mean by a graded algebra is an algebra that decomposes into subspaces AN. But if I take an element from AN and an element from AN, I get an element of AN plus M. And differential graded algebra means that it's also equipped with a differential T, which maps M forms to M. D of an M form is an M plus 1 form, and satisfies the Leibniz rule, perfect graded Leibniz rule. So, in particular, given any algebra, there's always an associated differential graded algebra, the so-called universal differential graded algebra, where the first component, omega 0a, the zero forms in the algebra, are just A. And then the rest of the algebra is the algebra generated by taking the elements of A and multiplying them together with formal symbols of the form dA, with the understanding that this D can be regarded as a linear map on the algebra that satisfies D squared equals 0 and satisfies this Leibniz condition. And so in particular, so another example of an element in this algebra is something that looks like A1, dA2, A3, dA4, and find out what order this is. I just count up the D's. So this is a 2 form in this algebra because it has 2 D's in it. Okay, and I just take products by smushing those together. So, to make a long story short, if you do this, there's good news and there's bad news. So we find that a bunch of other axioms appear to come from defining this algebra and now demanding that this guy is an associative star algebra. But what we really wanted to do was demand that this guy was a differential graded. So this guy was a differential graded algebra, differential graded star algebra. So the natural thing would have been to demand that this thing was also a differential graded star algebra. But for some reason, we couldn't get that to work. We were stuck. It contained extra so-called junk forms here. It's a well-known problem, and which prevented it from being a correct differential graded algebra. And then there was another problem, which is that, well, as John explained in his talk briefly, the non-commutative geometry that corresponds to the standard model is really a product of 2 non-commutative geometries. Okay, so the whole space is 10-dimensional, but it's a product of a 4-dimensional space and a 6-dimensional space. This is just 4-dimensional continuous space-time, and this is a 6-dimensional finite space. So the algebra is finite-dimensional, the Hilbert space is finite-dimensional. It's this thing I described over here. So if you do this construction separately to these 2 pieces, and just demand that D is associative, well, it turns out it works great in this space. Not only does it work great, it actually fixes a problem that there used to be with this space, where the axioms themselves didn't constrain the Dirac operator enough here, and so you ended up predicting too many scalar fields, too many Yukawa couplings, phenomenologically undesirable ones. But then, when we tried to apply the same associativity of D to the continuous part of the space, then whoops, it failed. So it seemed like this construction was too strong. It was either ruling out normal Riemannian geometry as a consistent geometry, or the statement was somehow that we were supposed to relax associativity. It was too strong to demand associativity. That even normal Riemannian geometry was somehow non-associative, which, is certainly not what we expected. Anyway, it turned out not to be the right answer. So then, in April, there was a follow-up paper by a group of French mathematical physicists, Bruder, Beasy, and Besnard. That's undoubtedly a horrible mispronunciation of this name. But anyway, this is a great paper. And
especially if you say it in French.
What?
Especially if you say it in French. There's no in French.
I see. Could we have the correct pronunciation for my future reference?
No. There's now some like I could try to tell you what it's something.
Okay. I apologize if you ever watch this on video. Again, I apologize.
You got a point.
Okay. So these guys solved these 2 problems. Okay, they showed that they basically solve each other. And what's the solution? Well, something we just didn't know about is that there's a well-known thing in mathematics, which is that if you have differential graded algebra, then the natural thing to demand of its representation is that it is a differential. There's a thing called differential graded representation, where you don't see. We were killing ourselves by demanding that the representation space here was nothing but the original representation space that A was represented on. What we should have been doing is taking some appropriate graded space here, where that's where H, the original representation space, was just one component, but then there were other components. And okay, so there's several things, several bits of structure that go into defining what a differential graded representation is. But that would have been the correct thing to do here. So that's the key insight that they had, that they show how to instead construct a differential graded representation of this algebra. And when you do that, you learn a couple of things. Okay, so first of all, now there is no problem that there are some so-called junk forms in here, and then there's some sort of induced junk over here. But you can that forms a nice ideal that you can mod out of this space and get. So you replace H by some appropriate graded space omega H. You mod out, and you now get a nice differential graded representation of A on H. And once you do that, well, now you can go back and re-ask the question about associativity. And now, voila, it turns out the continuous space is perfectly associative. Right action of any n form on here, and left. Sorry, if I take the left action of any n form on the representation space and the right action of any m form, that product now perfectly associates. So solving the junk and fixing associativity were really the same problem. And it turns out they recover a condition that we had found earlier, but as I say, really we were doing things wrong. So it's a bit of a fluke that it turned out to be the same condition. But so they find that in the associative case, associativity of the factored algebra, of the algebra where you've sliced out the junk, is enough to check these three conditions. That left action of zero forms commutes with right action of zero forms, so that's the order zero condition we found before. Left action of zero forms commutes with right action of one forms. So that's the so-called order one condition. That may be an axiom I forgot to write down here. Anyway, that's another axiom, and you get that. You get that in either formalism. And then the final thing is the left action of one forms and the right action of one forms commutes. So here, these guys commute exactly. This is the so-called order zero condition. This is the so-called order one condition. And this you would call it so-called order two condition. These guys commute up to junk. So they're equal to zero mod junk. Okay, and again, that is the condition that is satisfied in the canonical geometry. And if you demand that it's satisfied in the finite geometry, it provides a new extra constraint of the finite Dirac operator, which eliminates those unwanted extra terms in the finite Dirac operator, which gave extra unwanted scalar fields and extra Yukawa couplings that previously had to be set to zero by hand.
I think you've got minus something.
Okay. So I just want to say maybe one. I just want to make one thing. Just 1 minute. Okay. So I just to go one step further. If you apply this construction to the finite geometry in the standard model, well, I oversimplified in what I just said. I said it fixes it perfectly, fixes the finite Dirac operator perfectly, but then that's really not true. So the finite Dirac operator, remember this is in a finite space, so we have this 32 by 32 matrix acting on that 32-point Hilbert space. The finite Dirac operator is some 32 by 32 Hermitian matrix. And normal axioms of non-commutative geometry fix its form. So these are both 16 by 16 blocks. And this matrix delta is a symmetric matrix, and I won't get into the exact form of it. But the bottom line is the axioms set a bunch of terms to 0, but then they leave a bunch of terms non-zero. Okay. They leave a bunch of terms non-zero, some of which you want, some of which you don't want. So really, I said this extra condition, that extra condition exactly sets to 0 the terms you don't want. Well, that's not quite true. There's really 4 solutions to this condition, one of which sets all the terms to 0 that you want, and the other of which are unphysical solutions. So that's an improvement, but not the final thing. It doesn't quite get there. It doesn't uniquely select out the right thing. But now it turns out that it's going to be impossible to say. So if you take this, if you take the graded space omega h to be the simplest thing you might imagine, just the original h, and then an infinity of copies. So 0 forms and 1 forms, 2 forms, etc., are just an infinity of copies of that. And d, the d that acts on that is nothing but the original d, but block off diagonal, where in the upper off diagonals you have your original d. So now it's an order 1 operator that every time you act with this big D, the original D knocks you up from one space to the next. Then in the canonical case, if you apply this construction with this graded representation space to ordinary smooth the Riemannian spectral triple M, then it turns out that these 2 spaces are left, but once you mod out junk, everything of second order and higher is eliminated. So you end up with only 2 components in your graded space. But that is really exactly the statement, then, that although D, the original Dirac operator, does not square to 0, it squares to the Laplacian, this new D, the D that appears in the definition of the differential graded algebra, D, does square to 0, because it just squares to junk. And now if you demand that the same thing happens for the finite space, then you find that of those 4 conditions, of those 4 possible cases that we found before, only the one you want works, and the other cases don't mod out these higher spaces, so d squared doesn't go to 0. So I regard that as another bit of evidence that there is really something to this. That the basic structure is that the algebra, the data of the spectral triple and all the axioms can be neatly repackaged into the statement that this new algebra B is an associative differential graded star algebra, or super algebra, really. And so the hope is that that can give some insight into what to do next. In particular, there's the so-called BRST formalism, which is really kind of a machine for constructing such algebras and then turning them into actions and quantizations of those actions. The hope is that it'll give some suggestion about where to go next along these lines, but that is something we've just barely begun. Thanks, everyone.
We're quite time, so let's have 2 very, very, very good questions.
Okay, I have one question, but I really have 2 questions.
Well, so we can go to lunch. I should also say I didn't.
But just okay, maybe one is a simple question, just to understand this Heisenberg representation. If I give you a C-star algebra, my understanding here is that H now is just some kind of subcommutative algebra of that big C-star. So the question is that correct? Right?
You mean B is the C-star algebra?
Yes.
Oh, you mean, oh yeah.
So I'm trying to understand the reverse order.
You start with B and you say, when can I split it or something like that?
Yes, exactly. When is it? So I'm just trying to understand. In that view, H is just a subcommutative star algebra, and then what else do you need to
I
Okay,
don't know. I don't know the answer to that. Do you,
Seems like a
would you know if you were given a C-star algebra? Would you have any idea about when it could be split up into?
Based on C-star algebra. Yeah.
Well, certainly there is a
But if
whole,
you
in the context of KK theory, there's a whole theory of graded C-star algebras, that mod 2 graded C-star.
Yeah.
So that's definitely a very natural concept.
Okay, yeah. You know, I think I've heard Masood call these things square zero extensions or something like that.
In algebra, pure algebra, the original.
So there may be some theory about what algebras can be regarded as such.
Another question is it possible for you to give a little bit more an explicit description of this jump form idea?
Yes.
Like,
So the jump,
just because it's a key input into.
yes, and while I do
So-
that, I will cheat and take the opportunity to say I made it sound like everything was great, and there's actually a problem that I was hoping to mention to you guys. But so what is the jump? Well, so in non-commutative geometry there is the representation of one forms on the Hilbert space. Like I said before, is like this. You take commutator of the Dirac operator with the left action of A, and act that on the Hilbert space. That makes. So consider the and then if you had a two form, let's say, you know, A1, dA2, dA3, then in the associative case that would just be represented by the left action, the matrix that represents the left action of A1, and commutator of D with LA2 times commutator of D with LA3. Okay, so now consider in the normal, so what a jump form is, if this is the representation, then you can run into the unfortunate problem that there are non-zero elements in omega A. But when you represent them this way, the matrix will be zero, so they will annihilate H. But then if you take D of omega and represent it, it does not annihilate H. So the simplest example is in the canonical spectral triple, where D is really just an actual, honest-to-God, curved space Dirac operator, and the left action of A, well, A is just nothing but smooth functions on the manifold, and they just act on spinors by multiplication. So then here's a one form, this one form, FDG minus DG F. So in generating the algebra omega A, we don't assume that zero forms and one forms commute with each other. We're doing some non-commutative geometry thing. So this is a non-zero element a priori, but now when we actually represent it on the Hilbert space, this is just some function times commutator of the Dirac operator with some other function, and then minus commutator of the Dirac operator. This thing is zero. Okay? So omega 1, when you actually act it on the Hilbert space, vanishes. So that's an example of junk. But if you take D of this and use the graded Leibniz rule, this becomes df dg, and then because of the graded Leibniz rule, you can pick up a minus sign, so this becomes df dg plus dg df. So d comma f, d comma g plus d comma g, d comma f. Well, in fact, that ends up being a thing that's proportional to the identity. So you get a non-zero action. So that's the that's a two form that is non-zero, even though it's D of a one form that does annihilate the. So this is the sort of stuff you have to. This stuff. So you have to take your algebra omega A and mod out everything of the form omega or d omega, where omega annihilates H. That's what the junk is. And then once you do that, in the canonical case, you find that omega A becomes a new algebra, which is isomorphic to the normal Durham, like in normal exterior algebra of differential forms.
So that's probably all we can
Yes, sorry. Thank you.